We look at this example 2.10 last time. Let inside of the delta function equals to 0 and find the value of t. Put that value into here. So the first one, we have the delta t. Inside of the delta function t equals to 0, t equals to 0, put it into f of t. We need to find f of 0, which is 2. That's it. For delta t minus 1, we need to let this equals to 0, t equals to 1, put it into f of t. That means f of 1. From f of 1, that is 1. And for here, inside of the parenthesis in the delta, t equals to 0, put it into 0 here. 0 minus 1, which is negative 1. Negative 1 is a 3. And the next example that we're going to look at is this is not true all the time. This is true because we have 1 in front of the t. Now, if we have something else like a could be any constant 1, 2, 3, then it's not true. If that is the case, we need to take this out into the front 1 over absolute value of that, and the rest is going to be the same. Just like an integral of e to the negative t. We need to take 1 over negative 1, exponent of e to the function. We need to divide for the integral, just like that. Let's copy this down. So let's go through real quick. There are two different methods that we can try. The first one is changing a variable. So since a of t, there's a constant a, so we want to let a of t equals to tau, and then differentiation for both sides. Then the tau equals to a dt. Then you plug it in. Now we have 1 in front of tau, so we can use b, put it in here, sine square b over a minus c, and we have multiple of 1 over a. The second method we're going to do, you're going to do the time scaling. So we can factor out a, and in the delta function, we can take out the coefficient into the front, and that is 1 over a, and the rest is going to be the same. This is going to be just for your practice to dealing with the delta function. So next, you don't have to copy this down. This example, I want you to know how to add the signals. And we have 3u of t. 3u of t, this is the black line. We got, okay, we'll just plot 4 different signals in here. Don't copy it. You need to understand this. Don't copy it. Watch here. We got 3u of t. Any question about 3u of t? Is it straight? Okay. And magnitude is 3. And then second one, red one, is a tu of t. So t is going to be straight line going up. This is t of s, and this is y, right? So t, straight line, slope of 1, going from negative infinity to the positive infinity. And we're multiplying u of t. What is the u of t? Unit step function. U of t, anything below 0 is 0. Anything above 0 is 1. 1 times any given function is that function. So the u of t, unless we have the magnitude is 2, just like, or 3, just like the first signal, they are not going to do much impact to the other signal except for clear up the negative side. Right? So if you multiply these two, we have starting from 0 all the way to the up. So that's a red line, right? We got, and then the third signal, t minus 1, u of t minus 1. U of t minus 1 is 1 right here, is this. And then if you have negative u of t minus 1, just flip over x-axis. And then we multiply t minus 1. So this is the negative 1 slope of t, move to the right by 1. So that's the green. And the last one is the pink, u of t minus 2 times 5. So the magnitude is 5. We good? Now we can take a look at the y-axis. Look at the y-axis. There's a 0 for the pink, 0 for the red, 3 for 3u of t. Those are the 3 signals, right? They're in the y of x. Add them up. Now we have 3. That's the starting point. After that starting point, this 3u of t is not going to be impact to the rest of the graphs. So that's 3u of t is bring this signal up by 3. 0 to 1, this guy, we don't have to worry about it, starting point. And then this red one going up by slope of 1. And once you hit 1, there's 1 going up, 1 going down as a slope. They cancel each other flat. Okay, the rest of the line, they're all canceling out. And then when we have 2, it dropped down by 5. So 4 to -1. Now the last item from chapter 2, and system is a process for which cause and effect. Cause is the input, effect is the output, relation is the system model. You will see this type of diagram in control again. If there is a system, we have an input and output. In control, we're going to control this box. For these systems and signals, we're going to analyze the system inside of the box. In this and given system, when you look at system description, you should be able to say that system is memory or memoryless. The system is invertibility or the causal, time invariant, linear, or stable. So those are the 6 items that we're going to do. I gave you a couple of homework problems, and we'll do one today. There's a request for doing another one, so I'll put it another example next class. So memory versus memoryless. The book talks about all of this. This is my own word. Copy this down. You are not going to see this in the book. Memoryless system implies that the output does not depend on past or future. And then if the system has the memory, then we said dynamic system doesn't have the memory, static system. Output y of t naught at any time t naught depends on the input value other than t naught. That's the system has memory. It's a little confusing. So if the output depends on past or future, then it's a memoryless. How do we know? Let's say t equals to 0. Let's say t0 is right now. Then if t is 0, y of 0 equals x0 minus 1, 1. Output really depends on the past when t equals to -1. So this system is memory. Make sense? If you have y of t equals to x of 3t plus 1, and you plug it in y1, and then x of 1, you plug it in 1 is 4. Output depends on the future input. So that's the memory system. So in order to get the memoryless, you have to have y of t equals to cosine of t, for example. So you plug it in t as 0, 1, 2, whatever you put it in, we're going to have input x of t is the same time, the same t. Time invariant, we need to plug it in x t minus t naught for the x term, t minus t naught for the y term. We have these 2 examples. I think it is a good idea to put this example on your notes to compare. One is time invariant. This is time invariant system. This is time variant system. So what we need to do, y of t minus t naught for the output. So in the instead of t, we put t minus t naught for the output. Then the expression is x of t minus t naught minus 1. For this guy, y of t minus t naught equals to x 3 t minus t naught plus 1. First thing we want to check is putting t minus t naught instead of t. And then I'm going to call it y this time as a displacement of t. At this time, what we're going to do, within the parentheses of x, I'm going to just say minus t naught there. So from here, x t minus 1, and just subtract t naught. From here, y, the displacement or shift value of p equals x of 3 t plus 1 minus t naught. Now we want to see whether these 2 guys are equal. Now you see one is equal, the other one is not because of 3 in front of t. So this is, if they are equal, this is time invariant. They are not the same. So that's the time variant. Invertible. Invertible if distinct inputs lead to distinct output. So you need to test number of points. Every single input leads to different output. That's the invertible. So it's a good example. Y of t is t minus 1. This is invertible. Y0, Y1, all of those output associated with the distinct input. However, if we have a cosine t for x as an input, negative pi versus x equals to positive pi, there are two different input, but y of t is going to be -1, y of t still is going to be -1. So sine and cosine, they are not one-on-one, therefore they are not invertible. Linear. For linear, we're going to do x1 and x2 separately. We add them up, see whether that is equal to y1 and y2. So we'll have that example a little bit later. And you saw the circuit elements in the RL circuit. We learned that in the A-Math 1. That's the linear homogeneous equation. After we put this into standard form, dit over dt, we divide everywhere by L. R over LIT equals to 0, make it the homogeneous, and then find integrating factor, e to the R over L. That's the integrating factor. You multiply them and find the solution. Now the causal. So for the causal, we just need to look for the output is really depends on the future or not. So copy this down. All the physical systems are causal because the output does not depend on future input. Any given system in this world, the output cannot be depends on the future input. So that's why all the physical systems are causal. So all the memoryless should be causal. That is the subset of this condition. Stable versus non-stable. If it's bounded input give you bounded output, then that is stable. And then LTI system. So linear and time invariant. So that's a really important concept. Starting from chapter 3, all the continuous time signal, we're going to consider LTI system, linear and time invariant system. Let's do this example. Problem 2.31c. I gave you homework as a 31A and H. So we'll work on an C. Is this memoryless? The output should not depend on the past or future, right? So we need to look at the T. Output T, input T, they're the same. So it is memoryless and it is invertible. Yeah. So ln x of t is invertible. If you plot ln x, it looks like this. Any given input leads to distinct output. And we take the e for both sides, then e to the y of t equals to x of t. And that's the definition of invertible from x to y, y to x. So we can switch them around. But if the signal is too many components, it's not easy. Then you need to kind of visualize the signal or system, see whether they are one input according to one output. And then causal, well, we said memoryless. So all system is causal since it is a memoryless system. That's enough for the justification. If it's not memoryless, then you need to see whether that is, it's not depends on the future. Stable, it's not stable because when x of t equals to 0, it's undefined. So given bounded input is not giving us the bounded output. If you can find any single point that is defined as undefined, then it's not stable. Sine, cosine, e to the t, they are all stable system. Any given input, bounded input. Hey, Dr. Kim, e to the x, it's going to go to the positive infinity to negative infinity. However, any given input, you should be able to find the distinct output. That's the stable. And then time invariant, it is time invariant, just like what we discussed. You put t minus t naught for the t, and then just inside of the parentheses, you put the minus t naught. They are the same. Finally, it's a non-linear because of that. The linearity, we have y of t equals ln x of t. Now, ln x1 of t plus x2 of t. So what I did, I wrote x of t twice and one call it as x of 1, one call it x of 2, and then we want to have y1 of t, that is ln x1 of t, and y2 of t, that is ln x2 of t. Now you need to compare this equals to y1 of t plus y2 of t. They are not the same, so it's not linear. Let's take a look at this example for the linearity. So for the input, I would say x1 of t minus 1 plus x2 of t minus 1. That's the input terms. We add them up. And then we find y1 of t equals x1 t minus 1, y2 of t, x2 t minus 1. Now y1 of t plus y2 of t is the same as this guy. Yeah. We looked at this delta function last time. So that's the definition of the delta function. So book talks about, call it the shifting property. So we're going to filter them out. So the delta function is good function to sampling the continuous time to take any given interval. Convolution, the chapter 3 is a little short chapter, but it's all about this convolution. So convolution, definition of the convolution is this, and x of t convolution h of t, that's not times, okay? And it is convolution integral, and we're going to work more about it. Copy this down. So we're going to use this definition for our class, x of tau times h of t minus tau d tau, that is equal to x of t convolution of h of t. And let's work on this. Using the convolution definition, we want to work on x of t equals to u of t and h of t equals to u of t. So we have negative infinity to positive infinity, x of tau times h of t minus tau d tau. That is the definition of the convolution. X of t is given u of t. H of t is given u of t. So now we're going to plug this into here. X of t is what? U of t. Negative infinity to positive infinity. Then x of tau is going to be u of tau. So in here, our variable is tau, not t. For h of t is given as u of t. If you put it in here, we're going to have h of t minus tau and d tau. That h, u. What is u of t? Anything greater than 0 is 1. Less than 0 is 0, right? And the integral upper bound and lower bound is starting from negative infinity. However, in the expression, we have a u of tau. So anything below 0 is going to go away. It's 0. So this guy will give us the lower bound to 0, and that's it. Let's take a look at u of t minus tau. U of t is this, and u of tau is this. U of negative tau, what's going to happen? Positive tau is going to be negative tau. So we're going to have this, and then we're going to move to t. Gonna be, depends on the value of t. It could be this. So let's say somewhere in here, and we're going to call it this as a t. That means what? Until we have a t, we can multiply some of the function with the signal, but after t, it's going to be 0. So that'll give us what? Upper bound. So since it's a 1, integral of 1, it's going to be t. So it's a tau, I should say. Tau, and the upper bound t, lower bound 0, so it's going to be t u of t. That's the answer, t u of t. Or you want to split into two different, the reason, right? Then you can say either t u of t or y of t equals to t when t equals to greater than equal to 0, and 0 for t equals to less than equal to 0. We talked about it last class for u of t when t equals to 0. What is the value of u of t when t equals to 0? Discontinuous, undefined. We don't care. Okay? So I don't care you put equal sign here or not, or put it in the later. It really doesn't matter for this class, whether we have equal sign here, there, or not. Let's do this exact same problem. This time, we want to do using graphical evaluation technique. So we don't have to worry about this definition. You are given x of t is u of t, h of t is u of t. Before we actually tackle this problem, in the definition of the convolution, we say x of t convolution of h of t equals h of t convolution of x of t. That's true, but for the graphical method, I want you to use h of t as a h of t. You don't know what I'm talking about, right? For the graphical method, we need to change h of t to h of t minus tau. We have to change it. X of t, we can keep it. So first step, we need to draw h of t minus tau. That's the step number one. H of tau. Easy now. So this is h of tau. Step number two, h of minus tau. And step number three, h of t minus tau. So we need to move t to somewhere else, to the left side or right side. For this graphical method, I want you to move t to the left side, and we're gonna call it t. Always to the left side. For the graphical method, we're gonna have x of t is somewhere around this horizon. So we wanna have this t a little bit far away from x of t. Now what I'm going to do, we're gonna move this h of t minus tau towards to the x of t and find the area under the curve. So basically, we'll just look at the covering position, and if we need to take the integral, we're gonna find the upper bound and lower bound based on this graphic, not using the definition. So now we place u of t minus tau to the left-hand side. That's the step number 4. Now we have h of tau right there. We have x of t is right there. So now I'm moving this h of t minus tau to the right, and then we need to figure out the area under the curve, the overlapping area. Is there any overlapping? No, 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 no. Until we hit t equals to 0. When t equals to 0, it is undefined. There's no overlapping, because undefined overlapping with the undefined, we cannot find that. So we can say the first portion, say t is less than 0, y of t equals to 0. Overlapping portion is 0. And when t equals to greater than 0, we don't know where is the t, but when t is greater than 0, there are overlapping portion. What is the area here? T, base times height. So when t equals to greater than 0, y of t equals to t. That's the solution for the graphical, and the answer is the same as what we used for the definition of the convolution. So I gave you homework problem. Do the x of t, h of t as given in the textbook, and do the graphical method, find the solution. And then the following problem that I put it in, switch x of t and h of t, do the exactly the same, see whether you get the same answer or not. You'll be surprised. It's going to be a lot of different, but it's going to be good practice, because the chapter 3, this convolution, is really important, and that's the main component of this chapter 3. I give you the one problem for convolution on the quiz, one problem the convolution in the exam 1, definitely one problem for the final. Let's do this using convolution definition. Copy this down. So this time, x of t is given as a tu of t. Now it says using the definition. So we need to use the definition. Negative infinity to positive infinity, x of tau times t of t minus tau. X of tau is going to be tau times u of tau times u of t minus tau. So u of tau, we can take care of that for the lower bound. U of t minus tau upper bound. So it's going to be 0 to t. And then we have a tau That's the only difference. And when you take the integral of tau, it's going to be 1 over 2 tau squared. And going from 0 to t, it's going to be 1 over 2 t squared of u of t.